Today we present our work delivering arbitrary-modal semantic segmentation. RGB-only semantic segmentation cannot always extract high-quality features under some circumstances. For example, when two objects have similar colors and textures. So, multiple sensors installed on mobile devices can supply complementary information for the RGB cameras. Multimodal semantic segmentation models always outperform RGB-only ones. However, most works and multimodal benchmarks focus on specific sensor pairs, while the current trend is to fuse more and more modalities. That is, processing towards arbitrary-modal semantic segmentation. We have two observations when looking into arbitrary-modal semantic segmentation. Firstly, an increasing amount of modalities should provide more diverse complementary information, monotonically increasing segmentation accuracy. This is supported by our experiment results when adding up to 80 sub-aperture light field modalities. This potential is uncovered by previous cross-modal theory methods, which follow designs for predefined modality combinations. The second observation is that the cooperation of multiple sensors is expected to effectively combat individual sensor failures and partial sensor faults, which are common in real-life robotic systems. For example, LiDAR jitter fusing misaligned sensing data might even degrade the segmentation performance, as depicted with CMNeXt and HRFuser in the chart. These two critical observations remain to a large extent neglected. To address these challenges, we created an arbitrary cross-modal segmentation model, CMNeXt, and a multi-modal benchmark DeLiVER based on the color simulator. Unlike the previous multi-modal fusion architectures relying on the separate branches, which tend to be computationally costly, or using a single joint branch, which often discards valuable information, CMNeXt incorporates a novel hub-to-fuse paradigm. The computation cost will not increase substantially when adding more modalities. Our CMNeXt has an encoder-decoder architecture. The asymmetric encoder has 2 branches and 4 stages. We assume that RGB representation is essential for semantic segmentation, so the primary branch is for RGB and the secondary branch is for supplementary modalities. The RGB image is gradually processed by multi-head self-attention blocks, and we designed a parallel pooling mixer to process the images of other M modalities. Inside each stage, M+1 features are processed in the hub-to-fuse paradigm. At the hub step, M feature maps will be merged into one feature via the proposed self-query hub. At the fusion step, the merged feature will be further fused with RGB feature by the cross-modal feature rectification module and feature fusion module. After the encoder, the 4-stage features will be forwarded to the multi-layer perceptron decoder for the segmentation prediction. As mentioned before, we designed the self-query hub and parallel pooling mixer modules to achieve the hub-to-fuse paradigm. The self-query hub is crucial to select the informative features. A self-query module is applied to calculate the informative score mask for each feature from different modalities. The output feature of self-query hub consists of the patches with highest score among the modalities. The parallel pooling mixer is proposed to efficiently and flexibly harvest discriminative cues from the output feature of self-query hub. We use 3 parallel pooling layers to capture multi-scale model features. We then apply a squeeze and excitation module in the mixing part of PPX. It can engage more spatially holistic knowledge in the channels of cross-modal complements in the SQ hub. We also create a large-scale multimodal segmentation dataset DeLiVER based on the color simulator. The DeLiVER dataset includes 4 modalities: RGB, depth, LiDAR, and event, and 5 weather conditions: cloudy, rainy, sunny, foggy, and night. The complete frame of data is encoded in the format of a panoramic cube map, so we provide 6 views. For sensor failure cases, we consider motion blur over exposure and under exposure for RGB cameras. Due to fixation issues or rotational axis eccentricity, we add random angular jitter and position jitter to the LiDAR sensor. Due to the circuit design, the resolution of event sensors is limited, thus we add a sensor failure event low resolution. Each sample of the dataset is annotated with semantic and instance labels. We mainly discuss the front view and the semantic segmentation task in this work. The other views and instance segmentation can be explored in the future. To improve the class diversity of annotations as shown in the bar chart, we modify and remap the semantic labels in the source code. Specifically, the vehicle's classes is subdivided into 4 fine-grained categories: cars, two-wheeler, bus, and truck. To verify the efficacy of our CMNeXt framework, we conduct extensive experiments on 6 multimodal segmentation datasets. Here are the quantitative results on multimodal and dual-modal datasets. Compared to DeLiVER, KD360 only contains the samples on general outdoor conditions. In the case of sensor failures, multimodal theory makes more sense, and our CMNeXt achieves more improvement over the RGB-only baseline segformer. The experiments on dual-modal datasets show the effectiveness of our PBX architecture without self-query hub. We can see that our CMNeXt outperforms our baseline CMX even on the dual-modal fusion condition. As shown in this figure, in the 4 adverse weather conditions, RGBD fusion-based methods greatly improved the performance, particularly for distant elements in foggy and nighttime scenes. A failure case is shown on the right column. The RGB-only models has a better segmentation on the sidewalk class. In conclusion, we created a new benchmark DeLiVER for arbitrary-modal semantic segmentation and a universal multimodal network, CMNeXt, in the hub-to-fields paradigm, which achieves state-of-the-art results on 6 multimodal segmentation datasets. Thank you for your listening.